scientist, so congratulations. And he has joined the faculty at University of Toronto in the fall of 25. And today he will tell us about building a quantum simulator from stacks and twists. So please.
Thank you, Oscar. It's good to see a lot of people here. Yeah, if I don't talk loud enough, just remind me, right? Okay. So I'm going to start with a very broad motivation about quantum simulation, which is also the reason for why people like me have a job. And it is that it is the many-body problem. So if you try to specify a many-body wave function for n independent particle that each can be in d different state, the number of coefficients that you need due to very fundamental principle of quantum mechanics, which is just superposition and entanglement, is d to the n. So if you have spin 1/2, there's two states, so you need 2 to the n complex coefficients to fully specify the system. And then you can ask, if I have 75 electrons, the spin, how much memory would that take to store this coefficient on the computer? And it's already 200 zettabyte, which is more than all the storage we have worldwide. So basically, and this is just storing the wave function. It's not optimizing it. It's not finding it. It's just storing each of these coefficients with a float 32, or 2 float 32 per number. Right. Unfortunately for us, condensed matter theorists, most problems that we look at don't involve the full list. So the simplest of those problems are the ones I have classical. Think of a ferromagnet. Ferromagnet, you only need one of these coefficients at a time. It's either all spin up or all spin down. So I can store just I can store it with 1 bit of information and not 200 zettabyte. Right, and then there's then going more quantum. There are problems where the ground state of the system or the system is described by not one, but maybe a few of these coefficients. This is what I call low rank. We have all our mean field theories or Hartree-Fock theories, which basically are trying to reduce that entangled state with several coefficients to just a single coefficient, but seen in a rotated basis at every spin. Right. And unfortunately for me, the problems that I found the most interesting are beyond the limit of this low rank approximation, or just slightly beyond.
Like a pointer in a column.
Oh yes, yeah. But I like to wait. Okay. So in particular, the two I want to I may talk about are high temperature superconductors and fractionalized topological phases. Right, and on another day, I'm going to define all of that in a couple of slides. So on some other day, you will hear me giving a talk about how to expand the boundary of the low rank approximation down into the hard problem. So how do we find better computer simulate algorithm just to tackle this strongly correlated system where we need many coefficients to describe the ground state. But a different approach is actually pure. Okay, another time, because that's the discussion we had yesterday. You will see me finding exactly solvable model in that regime. Usually a single point with measure 0 in the space of hard problem, but that's the ideal wave function that we discussed yesterday. So and today it's yet a third approach, which is, can we take an experimental approach to that problem and try to simulate the hard problem with something that we control very well, and that's the quantum simulation aspect that I think can be done with van der Waals materials. The 2-slide introduction to quantum simulation is given by those few sentences by Feynman. So he just had a pristine way of saying it, but I think the idea was there before. So let's say you have a physical target, a system that you want to understand a bit better, but unfortunately for you, the system is hard to deal with experimentally, or you don't have full control over it, so there's still open questions. And the second thing that is not possible is to simulate it classically because of that exponential growth of the Hilbert space, it's not even possible to store the wave function of the system on your computer. So optimizing it and making numerical experiment on the target system is impossible. So all you have to do in those cases is find an analog quantum system over which you have a much finer control. So you can do more experiment, draw more data out of it. And that analog quantum system should also be close enough, or you can bring it close enough to the original problem, either by tuning some knobs of your experimental setup. So that seems easy to say, at least easy to write. The usual bottleneck is experimental here. So it's to find a good system over which you have enough controllability and experimental knowledge, right, to be able to extract more property than you would from the original target physical system. And the second thing that you also need to make a good quantum simulator is that the same platform should be tunable enough so that by changing a few free parameters in your lab, you can just create Hamiltonians that are close enough to interesting problems. But yeah, whenever you think you have a good enough platform that satisfies roughly these two constraints of controllability and tunability, then you can hand your system to a theorist that will tell you what kind of Hamiltonian you can engineer with your system and what are the physical targets that you may hope to reach. Right? And basically, this is the outline of the talk. I'm just going to highlight how this can be done, how quantum simulation of topological phases can be done with van der Waals materials. I'm going to drive you through why are they good platform for quantum simulation, how you can think about engineering topological phases in them, and how, what are the conditions to operate your system to actually simulate the system. So all of that will be about topological phases, which I need to spend a few minutes defining. And usually this is the part of a condensed matter talk on topology where people try to trick you into believing that condensed matter theory is the study of coffee cups or donuts or things like that. But actually there's really a notion of topology that's easy to understand. So I really want to just drive you through it for a few minutes. So we're dealing with electrons in a crystal, right? And because translation symmetry is continuous translation symmetry is broken to a discrete translation symmetry, we still have a crystal momentum as a good quantum numbers. And then quantum mechanics tells us that for each crystal momentum, we have a finite number of energy states. Those energy states form, as a function of the momentum, some bands, right? And the electrons live on a localized orbital on each of the ions of the lattice. So, they have a different orbital character at each of the crystal momentum. Right? And we are interested in the transport. So how, if I apply a difference of potential to my system, how do the electrons flow? And so answering that question just naturally make you describe the velocity of an electron that has a specific crystal momentum at a specific point of that band. And if you compute that velocity, there's two contributions. One, which is the electrons follows its band. So that's the blue line here. And that's the standard equation of motion, Hamiltonian equation of motion. So you have some energy profile. You differentiate with respect to momentum, you get the velocity, right? And there's another piece, which is actually an interband contribution. So as you move, you can also be sent up to a different energy state. And this is, for instance, you were on a d orbital, and the d orbital is on a different band. So, as you move, you carry your orbital content, but you're sent in to another band. So these are the two contributions.
What is that?
A here is what we call the buried connection. It just pops up naturally when you compute that. But yeah, the important part of that, yeah, okay, yeah. So, and this is how it relates to Berry curvature and Chan number. But it's just some number, some vector. The interesting thing about it is that if you take the curl of the velocity field, now the first term, that is the regular Hamilton equation of motion, doesn't have any curl. It's a gradient. But the second one can have some curl. And so if you plot that curl, or here I plot A and the curl as a color plot, then you see that the velocity field can have some winding, so some vortices. And vortices are topological objects. So you cannot smoothly deform a vortex and remove the singularity at the center, right? So you cannot.
Is delta E, is that a band gap?
Yeah, it's a band gap. Yeah.
So the velocity depends not just on the very curvatures of property of the actual band, but actually velocity depends on the band gap up there.
Yes. So here the A is only interband, and delta E is the difference of energy between the band you consider and the other ones.
Yeah.
And it's some of all the bands that you're not looking at. Yeah.
Why when the gap is bigger, the velocity is bigger?
Yes. Okay. So it's just also the matrix coefficient decreases. So there's a sum rule. If you actually compute an observable, let's say current correlator, so you have a delta E, but you go to a higher band. So when you come back, you will have 1 over delta E from perturbation theory, and the two cancel out, give you another one number. So mathematically, this is how, this takes a while. Yeah. Yes. No. So it's just the formula of the velocity, and then if you're trying to compute something, this is an interband velocity as well. So if you compute current correlation function, only the two-step processes here will matter, and there will be just another one contribution to this if you do the math. Right. No. Oh yeah.
Is that kind of like a Kubo formula?
Yes, if you do that, yeah. But so
Same.
yeah. So there's a delta E, but nothing actually diverges as you go to higher and higher bands. Okay. There's nothing. Yes.
Don't delta E have to be in denominator generally? You have some interaction brings you to higher band, and then you go back and then standard piece.
Yeah, so that's and so the coefficient that brings you up is this coefficient, and then you will have a denominator, and that denominator is regularizing all of the quantity, physical quantity you can extract from that.
Where will I have a denominator?
Excuse me?
You said I will have a denominator. Where?
Yeah, if you compute any response function. Yeah.
So in addition probability.
Yeah.
Something square. Me A there is that number.
What's that?
In the very connection there is a denominator.
You want so it's a really simple, silly thing. So you want the derivation of that formula? So it's really a silly thing. It's just I'm saying I have a Hamiltonian. I diagonalize it. It depends on some parameter. Okay. And the velocity field, right? It's just nabla of H. H in an orthonormal basis is sum of En and N. Right? So the first term, Hamiltonian equation of motion, is I differentiate that term. And the other one is delta E, just because this one is an eigenstate. Right? So if I sandwich over M and another one, M prime, so I get something that is M prime nabla N. This is my A, times the energy of M prime. And then minus, if you use the normalization of the function, EM, and here I have N and M, this, and then, all right. So this is just where it comes from. So it's just recasting defining Berry curvature, but there's no actual meaning. So if you define these differently, the delta E disappears. If you don't want the delta E, you can just take the energy here to be an energy. This is proportional to an energy. This is proportional to an energy. I need an energy in the second term to make something that is dimensionally correct. Okay, so there's no. Right. It's just the current. All right. Sorry. All right. So maybe I'll hide the delta E next time. But so there's just some piece that has some that doesn't have any curl, and another piece that has a curl, and all of them need to scale as energy terms. So there's an energy in both cases. A here is dimensionless, so I need to. It's 1 over k. So the energy needs to be as a prefactor of A. Okay, and the topology arises from the separation of V. So if I apply a displacement field, what happened in the case where I have pairs of vortices and anti-vortices, or I don't have any circulation as I integrate my curl along the Brownian zone, then most of the current is going to average out between the line that go up and the line that go down. I'm only going to have a current in the direction of my difference of potential of my electric field or the electric field that arrive. But if I have a sum vortex in the Brownian zone, then the current will not only have a longitudinal component, but also a transverse one. So these are just images, but it's just to let you know, there's a concrete definition of topology, which is, if I look at the curl of the velocity field, there's vortices or no vortices. And then there's a physical consequence to those vortices, which is if I apply a displacement field or an electric field, I will have a current in the transverse direction. And the current in transverse direction will be proportional to the number of vortices because circulation around the vortices is constant. Right. And this is, so those were a picture. It was actually proven proved by TKNN in 1992 that indeed, if you look at the transverse conductivity, the latter is quantized in unit of E square over H. And the number C here is exactly the curl of A that I introduced above. So that's why we decoupled this way. For an insulator, this is for an insulator. And for an insulator, the transverse resistivity is high, or the longitudinal conductivity is, okay, resistivity is zero, is high, sorry. Longitudinal resistivity is high. So how you can understand this transverse conductivity is through the edge channel in your system. The bulk itself is insulating, but you still need to satisfy the curl condition. So the only place where the system might be capless and carry the current from one edge to the opposite edge is through edge current, and then C can be thought of as the number of edge modes that you have in the system. Okay. And then so this is fairly well understood. What is much more difficult to understand is if you take the same like a topological band and add interaction. So now I'm going from one of the simple problem that can be described with a single coefficient to a problem that becomes extremely difficult to describe theoretically. That number, the C number, can become a fraction. And that fraction is understood after the fractional quantum Hall effect and all of the pioneering work to understand it afterward as a fractionalization of the electron into new types of quasi-particle that carry fractional charge. And because they carry fractional charge, they also need to carry fractional statistics. Okay, and those are called anyons, and they are envisioned for topological quantum computation. So many people are interested about those. But what I'm trying to say here is there are a system where with fractional topological number, it's hard to describe them, and it's hard to get information over them. So we would like to get a new system that is flexible enough and would bring us more insight into those systems. And that's what I'm going to try to simulate in that talk, just as an example of what you can do with van der Waals heterostructures. Okay. So that was for the introduction. So is the motivation okay? Yeah. So if the motivation is okay and you followed my quantum simulation plan, the first thing I need is a good quantum experimental candidate. So something that is tunable and controllable and over which I can make a lot of measurements. And the rest 20 years or a bit less, or so. One such platform has emerged. It's van der Waals heterostructures. They've emerged after the exfoliation of graphene around the year 2000. And van der Waals heterostructure are just layered material that you've exfoliated and put back on top of one another. So they just look like a regular material, except that between the layer, you now don't have any chemical bounds to satisfy. So there's no chemical links between each of the layer. So they are not so much different from the semiconductor thin layers that we know how to make. Here you get a picture of gallium arsenide, aluminum arsenide, which also are a few layers deposited on top of one another with another technique. The main difference is there's no chemical bond to satisfy between the layer. And in the 3D bulk material, because you have those chemical bond and because you don't want to introduce strain, defect, or things like that at the interface between the two materials you proximitize, you can only grow systems that are pretty much alike. So here you substitute only one element and you can make a heterostructure of that form. But if you don't have any chemical constraint to satisfy, you can basically put anything on top of anything else, giving you more freedom. And that freedom allows you to really expand your toolbox, because you could think about putting a superconductor on top of a magnet or a semiconductor on top of I don't know, a metal and see what happens. So you definitely have more choice now. And how many choice is there's about 2,000 exfoliable material that we know of theoretically. That range from metallic, semiconductor, insulating, some are superconducting, also in the monolayer limit. So there's many things that you can do. Just one example of something you can do is put graphene on top of a material that has a strong intrinsic spin-orbit coupling. So graphene was envisioned for a long time as the next generation transistor, but it's always hard because there's no gap. So there's always some leakage current, and you would like to open a gap. And one way to do that is just add some spin-orbit coupling onto graphene. And just by proximity effect, you can just deposit a bit of graphene on top of MOS2. So this is just a material with spin-orbit coupling. That's big atoms like molybdenum. And that's enough to open the gap I was measured here in graphene through Cherenkov-de-Haas oscillations. So you get just 2 peaks is all you have to see. So there's some opening of the gap, which is what people wanted to do.
What was the magnitude of the gap in energy?
Oh, I get back to you. So, but it was extremely small. Yeah. Which is a bit, yeah, okay. Okay. Yeah. Okay, and the second thing that condensed matter physics has traditionally done to expand the toolbox that they have at their disposal is to do superlattices. So if you are stuck with aluminum arsenide and gallium arsenide, you can still do like 1D superlattices of the structure to get a laser, while none of the quantum wires by themselves is lasing. And so creating those superlattices give you another knob to change the physics of the system. And this is quite fortunate because if you look at heterostructure, they generically have those long period superlattices, which we call Moiré superlattices. And this just comes from the fact that the 2 layers that you put above on top of one another don't have the same lattice constant. So they form like this kind of long wavelength interference pattern. And the fact that you have an interference pattern doesn't tell you that they are useful for anything, as they were for quantum wells. But what started the field of Moiré materials was an experiment in 2018 that shows that having those superlattices could really change the physics of the system. So by taking 2 layers of graphene and twisting them by about 1 degree, you could get a superconductor while none of the monolayer by themselves is superconducting. So it just tells you that, that it's one more knob that you can play with to get tunability or to access new physics from like a stacked monolayers. Right. And I want to pause and tell you about controllability, because so the first 2 steps of the reasoning was I need something that is tunable and versatile to be able to map as many Hamiltonian as possible onto my system. The second thing is I need to extract information from it. So I need those systems to be controllable and measurable, or that I have ease of measurability. And what you should take out of that picture is basically that the entire phase diagram was obtained with only one sample, M2 here. And so it's a single sample and you get the full phase diagram. And you should compare that to the traditional way we got phase diagram in condensed matter with 3D bulk is by changing some parameter as we grow a material, so typically the doping or conservation of some atom for many material family, and then we project that onto some hyperplane, and we hope that all the data is consistent and make a consistent whole. So that's, for instance, the phase diagram of the couplet, and here you get something that pretty much look alike, but still in one sample only. So it allows you, and the reason for that controllability is that if your system is two-dimensional, you still have one direction of space to engineer something and control the system. So in that case, the material was just put in a capacitor. By changing the gate voltage on the capacitor, you can change the chemical potential. And by changing the chemical potential, you change the carrier density or things like that. Right. And for the ease of measurability, let me just mention that all of the tools that we had previously that were just probing the surface, now because your two-dimensional surface material is a surface, is basically probing the entire system. So all of the non-penetrating microscopic tools are just now, probing the entire system and giving you all the information, a lot of information about the system. So there's more probes that you can also play with for these two-dimensional materials. Okay, the problem with them is there's about 2,000 material. So if you just look at bilayers, there's 2,000 possibility times 2,000, which is 4 million. And it unfortunately take about 6 years of Oscar's time to explain the experimental data at one particular filling in one of these particular material. And so there's not 4 million Oscars out there. So all you can do is try to hope for a better way to guess what the system is going to realize in advance and try to design new tools. So typically, you can also try to get the band structure, so the spectrum as a function of crystal momentum in this big unit cell. But because there are a lot of atoms per unit cell, about a few thousand, this calculation takes a long time. So every one of these plots takes about 3 weeks to run on the cluster, when usually with our code, we expect them to run for, I don't know, 10 minutes or something like that, for regular material with only a few atoms per unit cell. And so we'd like to find a way to predict what's going to happen without having to spend I'm deforming the reality, but without spending too much time and trying to give to shift from a reactive approach where we basically try to understand the data to giving hints on how you may simulate a specific Hamiltonian, which I now turn to. What kind of material should I use if I want to realize topological phases, right? So these small vortices in the Brillouin zone. Right. And let me take two specific examples. So let's say your lab is specialized into patterning a dielectric, so with some technique. And then on top of that pattern dielectric, you will put a two-dimensional material. You apply a gate at the bottom, and that will produce a long wavelength superlattice. So it's basically the same as it's the toy model for a Moiré material. Right. So if this is the tool that you have at your disposal, how can you realize a topological band or anything that has a quantized chain lambda? And then using that, I will just do the same thing for homobilayers, twisted homobilayers, but the idea is the same. So what happens in that case is quite simple. So you have the 2D monolayer that you put on top of your pattern dielectric. The dielectric introduces a superlattice. The superlattice period is large, so the Brillouin zone, the Moiré Brillouin zone is small. So you fold all of the dispersion into that new Brillouin zone, so the inequivalent crystal momenta, and the harmonic of the superlattice potential are going to open the gap at the edges of your Brillouin zone. Right? And all you have to remember for the sake of that talk is that you can obtain the gap at the edges of the Brillouin zone and the wave function at the edges of the Brillouin zone with perturbation theory. So just, you know the shape of the superlattice, so you know the harmonics, and then you do perturbation theory in those variables, and you get the wave function and the gap as a function of what you apply, and the monolayer coefficients. Right? And so if you have sufficient symmetries, the vortices that I was discussing at the beginning of the talk cannot appear anywhere. So if you have C3 symmetry, the vortices in the Brillouin zone can only appear at C3 invariant points, which are the center here and these 2 points that we call K and K prime. And these are precisely the points where the gap opening happen when I add the super harmonics of the superlattice perturbatively. And because I have a wave function that I obtain perturbatively at those points, I can then try to look at the property under C3 rotation. If they get a phase, then that means that they are at the center of a vortex. If they don't get a phase, that means that there's no vortex at that point. So by just looking at those perturbative calculations, the result of those perturbative calculations, I do a C3 rotation. I basically predict how many vortices and what's the vorticity at the edges of the Brillouin zone, the corners of the Brillouin zone. And from that, I can get the Chan number. So mathematically, this is described by something that we call topological symmetry indicators for topological invariance, right? And it allows you to get phase diagram like so. So it's too many information, but basically, if you followed what I've said so far, is from the harmonics of the superlattice potential and a few material coefficients that I combine as a product, I can get the Chan number of the system composed of the 2D monolayer, the Chan number of the mini bands for the system composed of a monolayer and a superlattice potential. So yeah, I can give you one example. So let's say I apply a superlattice potential that is triangular, that has C3 symmetry. Then I can start either from a triangular superlattice potential, and let's say I don't have any barrier curvature. And this is in the trivial region. If I start from a honeycomb potential, I start at pi here, and my system is gapless, so that's the Dirac cone of the honeycomb lattice. And you have to trust me on that, but as I increase the barrier curvature in my system, I move along the first diagonal of that plot. So out of the triangular lattice, it's very hard to stabilize the topological phases. I stay in the red regime, which is trivial. But as I add a tiny bit of barrier curvature to the honeycomb lattice, then I end up in a topological C equal +1 or -1, depending on the side of the barrier curvature. And that reproduces the original result by Haldane.
So you're talking about introducing a barrier curvature
to the monolayer, yes, exactly. No, not the superlattice. So that would be in the form factors of the monolayer that you put in this calculation. Yes. All right. So you can use the same strategy for the twisted homobilayers. Then it's slightly more abstract, but the same strategy holds. So what you want to know is what is the superlattice, the geometry of the superlattice Hamiltonian. So what will be the harmonics that will couple the corners of the Brillouin zone. And for that, you just have to ask how big is the interlayer tunneling, for instance, at specific points of my Moiré Brillouin zone. So if I know the tunneling at that point where the two lattices are on top of one another, or when they are shifted by a third of a lattice constant, then I can determine the few first harmonics of my superlattice potential. I combine it with the material coefficient as I did before, and then using my symmetry indicator formula, I know if there's vortices or not, and I count the number of vortices, I get the Chan number. So you can do that systematically for all of the 2000 material listed in the database. And one example of that is if you only take the semiconductors with C3 symmetry, you can ask what is the Chan number of the bottommost Moiré valence band and the topmost Moiré conduction band. And you get just a value for the gap, which is the perturbative opening at the corner of the Brillouin zone, and the value for the Chan number, which is here represented with the color. So you get a non-zero Chan number for the red materials here, and a trivial Chan number C equal to 0 for all of the other ones. So the empty symbols.
These are all twisted bilayers?
All twisted bilayers, yeah, twisted homobilayers. Right. Okay, and this list is actually you can learn a lot from it. So if you wanted to quantum simulate topological phases, you would go for materials that have a strong topological gap. Okay, but you could also say, can I look at something related to superconductivity? Then you go through the list here of and you look for superconductors, and there's one right here, nitrogen chloride, which has a large enough gap. So that, and by opening the gap, you increase the density of state compared to the monolayer, so by about a factor of 4 for that material. And so you could increase TC by a factor of 4. TC in the monolayer material is already something like 13 or 15 Kelvin. So going all the way, increasing it by a factor of 4 would actually put you in the strong coupling limit, where the Fermi energy, and TC would be comparable. So, but this is heuristic, but we started looking into it. Yeah.
Yes, we don't need to know the entire energy spectrum at this high symmetry point.
Yes, exactly. So you all the only thing that we need is the fact that they are high symmetry points. So the energy at K and C3K is the same. And
It's very what does it include? Like, what do you consider? Like, you consider
so monolayer form factors. So whether there was some Berry curvature to begin with in the material, that we consider. And the second thing we consider is what is the shape of the superlattice potential. So if it's honeycomb, then it's easier to create a topology. But it could also be that the superlattice potential by itself has when you have more than just a 1 degree of freedom and you have a spinor, then it's possible that just interlayer coupling by itself induces topology. So you don't need form factors in the material. But these are
atoms, like different materials, play a role here.
This is abstracted out in our DFT. So that would, if the right. So the different atoms, how they play a real role, like on the microscopic scale, it's just how big is that tunneling. So if the atoms don't like to be on top of one another, they will go further away, and that tunneling will be smaller. So how atoms are, the atoms you manipulate basically change the geometry of your coupling on the Mori scale.
So
It's interlayer here. We also have intralayer components, but there. So the chemistry is in those harmonics, is in the harmonics of the superlattice potential, basically.
How does the reconstruction enter into this?
Yes. All right. So I really like that question. So you see, it doesn't enter, and the problem is I've done that perturbation theory, and within perturbation theory, I've included the highest harmonic because that's the one connecting K to C3K. So all of those results are only valid as in the high twist angle limit, but the only thing that matters is the first harmonic, and So we have a way to there's a dimensionality parameter that tells you when I should have put it. It's in our paper. So we have a way to characterize when does a lattice relaxation sets in and invalidates our perturbation theory. It's usually for all of these semiconductors about 2.5 degree. So higher than TBG, but because lattices are less stiff, it's big atom semiconductors. So yeah, within the range of 2.5 or to 5 degree, you can trust this gap. And we've actually done continuum model and tried to add lattice relaxation. Interlayer relaxation is effectively included because we run DFT at different stacking points. And so for each of these stacking points, we allow for relaxation in the Z direction. Right. So intralayer is not included. And intralayer sets in at between 2 and 3 degree. So below 2 and 3 degree, you cannot trust that data. Yes.
That data you can't trust at such small angles only because a single harmonic in the potential is sufficient.
Yes, exactly. So it's actually, so since I manage my time poorly, I'm just going to say that. So it helps actually to have some interlayer, some lattice relaxation if you want to stabilize topology. So what we've realized is if we look at the renormalization of the first harmonic when we include lattice relaxation, we saw that the interlayer tunneling was decreasing at the center of the unit cell in real space at AA, just because that region is shrunk when we include lattice relaxation. And that generically helps creating charges, localizing charges on the honeycomb lattice, which is good for topology. So if you take, we did it for several materials, but the one I remember is this one, which is topologically triggered. If you include lattice relaxation and redo this calculation, it turns topological, in fact. So there's an answer for including the lattice relaxation, so it's not full-scale calculation, but generally it helps to get a bit of relaxation for topology. Okay, yeah.
I noticed that you have lots of topological guys at small gap.
Yes.
Right. But small gap materials are extremely sensitive to disorder.
Yes.
So does it make sense?
Yeah, so basically all of those topological materials, so the one with zero gap, I wouldn't even try to use. It's here, whenever you have disorder, I don't know what you would do with those materials. And there's a lot of disorder in those twisted structure, maybe not a 5-degree twist angle. So I would advise anyone doing an experiment choosing those one. Yeah. So, but this serves as a guide. So at least you know which one to use if you want to get some topology in your system.
Yeah. But, graphene is clean, but all other materials are dirty.
Yeah. So I'd say, okay, so if you just look at here's my balance bands MOTE2. So the channel number 1 here was measured for a gap that is about 1 MeV. 1 MeV is still 10 Kelvin. So it's just one is small in our head, but still 10 Kelvin. Yeah. Okay, so I took too long. So let me just say something else, which is precisely what I just said. So this is twisted MOTE2, which we predict, like our table says it has a topological band gap of about 10 Kelvin. And that's indeed what has been seen. So the state at mu = 1 here is a ferromagnet. It lives in a band with channel number 1. And when people did transport, they indeed saw the sigma xy quantized in unit of equal to E²/h, right? With no longitudinal resistivity. So that match, at least we were happy our data match what they found, right? But the problem with that material, is that, okay, what limits the TC in this material is that you need to fully polarize the system to see the channel number. Otherwise, if you had spin up and spin down, you would have by time reversal invariance, the contribution C = 1 from the spin up and C = -1 from the spin down. Overall, no topology or no clear edge modes. And to polarize the system, you need to go below 10 Kelvin, typically, I think it's 13 in the experiment. But what really limits the stability of your state is this Magnon gap, so the spin flip energy. And it's not the true gap that I was showing above, which is about 2.4 here. So if you really want to push this topology to higher temperature, you also need to care about how is time reversal symmetry broken in my system. Is it spontaneous, as in this material, so driven by interaction? Or can I find another material where it's broken by a stronger effect? And again, you can go through the list and you find a close cousin to MOTE2, that's chromium ditelluride, and chromium has strong nuclear spins on the chromium, which can order very easily. So those ones, if you order them magnetically, they will break time reversal symmetry at much higher temperature, typically. So I think in the few layer limit, 5 layer was shown to be ferromagnetic up to almost room temperature, so 250 Kelvin. Right. And in that case, what will limit the stability of your system is the true gap that I've extracted here, so the single particle gap between the two Moiré bands. And it turns out that this one in our calculation has a has a gap that's 6 times larger. So again, if you really want to simulate topological phases, or at least topological band, this is the one material I would advise you. I would advise to use, at least from this small scale calculation. Right. Okay, and I haven't had the time to discuss fractional state. I still have 10 minutes. I think I can. Very still good.
Yeah.
Okay.
More than 10.
Well then, oh yeah, full hour. Okay. So the second point I want to raise is, now that we have found a system that have quantized transverse conductivity in unit of E square over H, but at least quantized to an integer, how can we, what are the operation we need to, what are the conditions in which we need to operate those systems to see fractional topological phases, which were from the beginning my physical target. And so these are, I just put that as a riddle because it's the end of the talk. So these are 2 experiments split in time by only a few months. It's actually the same device that was observed. So that was, it was the first experiment. Okay, so you see what they do is circular interferometer, which measure the amount of time result symmetry breaking in the system. And so red means that the system is magnetic, and white means there's as many spin up and spin down in the system. New is the doping concentration. So they dope holes into the twisted MOT2 sample. And they can also add the displacement field out of plane that creates an interlayer potential difference. And so they see something that looks ferromagnetic in some part of the phase diagram. And the question is, a few months later, they basically get the same data, much better results, and they see this tiny dip. And that tiny dip was the first hint of fractional channel insulator, or fractional, the analog of the fractional quantum Hall state that I was discussing at the beginning. So yeah, so I'll put it as a riddle. Would you have guessed to look precisely there? So there can be a push to just get cleaner data for the sake of getting cleaner data. But what instructed you to look there and not change material, pick a different one, and try your luck with a different system?
Are we supposed to see a stepwise change?
It's just a kink here. And they measured the position of that kink as a function of magnetic field. And this is what gave like this Nature paper, which was the first. So if you look at the position of that kink as a function of magnetic field and density, you see it follows the straight line. And that is a sign that it behaves more or less as a fractional quantum Hall state. That's also what you expect for fractional quantum Hall state. You change the magnetic field, you need to the density of electron need to track the value of the B field with a specific slope, and that slope was giving you anyway. Right, so you need the ID. So to make better data, then put a magnetic field and do all of that. And so the question is, why would you do that? I think it's again from very generic. Okay, so you can do hard calculation, but at the end of the day, the answer to that is phenomenological. So if you do calculation on a system that tries to describe the twisted MOTE2, what you see is indeed a large portion of the phase diagram is dominated by a metal. So many states here, it's a continuum. That is ferromagnetic, so the full spin polarization are the red lines here. So what you see is a ferromagnetic metal. At nu equal to 1, it's no longer a metal. You've completely filled the band, and so you have the quantized sigma xy insulator, the channel insulator here, right? Right. And in all of this part of the phase diagram, there's a spontaneous breaking of time reversal symmetry just because you polarize all of the electrons into one of the spin components. Right. The intuition for why is you get a flat band. If you really have an exact flat band and fully fill it, it's better to fully fill one of the spin component only if you have local interaction because of Pauli exclusion principle that prevents you, like you win. You don't pay any kinetic energy if you have a flat band, And you also don't pay any interaction energy if interactions are local.
Are you talking now about explanation of experiment or prediction?
Yeah, so that was in between the two experiments. So that
So it was not a prediction.
it's a prediction. It happened in between those two events. Yeah. But it's a long time ago. I don't know. It served as a motivation, I think, to look at the data more precisely near the fractional filling. But yeah.
Explanation and prediction are different things, right?
Yeah, that was the theory appeared at the same time as this paper. So it pushed, I think yeah, never mind. It may have helped or not helped. Yeah. All right. Okay, and you have this ferromagnetic metal all over here, and the question is, what can that ferromagnetic metal turn to at very low temperature? You can think of the standard instabilities of metal. So, for instance, superconductivity. And superconductivity, unfortunately, is hindered for time result symmetry broken state because you would need to pair in P wave, and the P wave gap is small. Oh yeah, okay. So it's just a regular thing. And so then you can think of breaking other symmetries and not only charge conservation as the superconductor do. So the other symmetries you can break in the system are charge density wave, translation symmetry. In that case, you would form a charge density wave or just a translation symmetry broken state. The other competing state is a fractional chain insulator, so the fractional quantum Hall analog that I was discussing above. Just by running the calculation on the specific model we had, we found that at filling fraction 1/3 of that band, so when we fill 1/3 of electron into that band, the system remains ferromagnetic, and this is the one that is favored. But you can also take that as a you can just check that prediction. Yeah, and the competing state at that filling is a charge density wave. The two have different sigma xy, which really push you into measuring that Hall conductivity. And the way to measure that conductivity is look at that particular filling, apply a magnetic field, and measure the dependence of any quantity as a function of magnetic field at that filling. If they are independent of filling, then probably you have a state without any Hall conductivity, so it's a charge density wave. If you see that things move as a function of magnetic field, then most probably you have a response with a non-zero Hall conductivity, and you more likely are in the fractional chain insulator scenario. Yes?
Conceptual question.
Yeah.
You just phrased it as one state or the other state. Do you have predictive power in your calculation to say which state has a lower energy?
Yes, in our calculation, it was the FCI, the fractional chain insulator, the quantum Hall analog. And actually, it was a very decent gap. And surprisingly, so usually those things don't scale as well. So between the two system size, it's very small system size. It's about 30 sites that we can do. But the gap doesn't change as a function of the 30 versus 24 sites. So it's more robust than the level that was the toy model in the 2010 to look at those systems. And this is due to the band is so flat that it was extremely robust. So for us, it was really a surprise that it was that robust. Right. But okay, so we have predictive power, but we were wrong though. So I think fraction 1/3. If you look at the experiments, there's no ferromagnetism. So we were probably using interaction that was too big. But there's still, if you look at the density range in which ferromagnetism appears, 2/3 is in there. So you could still ask the question, well, it's a fractional filling. So there's a competition between the charge density wave and the fractional quantum Hall analog. Right. And but for that, you need to do the experiment. And the experiment showed that it was indeed the fractional quantum Hall analog that was lower in energy and stabilized. All right. I think then I'll probably 5 minutes. Okay. Right. That is too long. That is too long. Okay. So I'll stop there. But okay. So I think if I got one message through is that the van der Waals heterostructure are extremely versatile. So you can try really to play with what you put in contact. So that was the goal of my long list of materials of homo bilayers. which one are topological, which one are not topological, then that would allow you to select good material for desirable properties. And then once you have that material, the question is, under what conditions should you operate them? And one hit is just look at some phenomenological toy model and try to provide some guidance to experimentalists for look here and not there. So that was our failed attempt to look at 1/3, but it 2/3 basically worked out. So it was good in the end. Right, and that's all I had to say. Yeah.
Time for more questions. Yes, Alex.
Thanks, Valentin. I have a question that I feel like would have been answered in your last section. Maybe it'll allow you to give a miniature version. So exact diagonalization, you said it worked in this case because you could satisfy yourself with the small unit cell because the bands were so flat. So were you going to hint at some way of doing for some way of predicting fractionalized excitations, systems for which you will have fractionalized excitations? That's the analog of what you successfully demonstrated using the simple perturbation theory.
Yeah,
Is
so
there a recipe that you can resort to?
right, this is very hard because then you're asking a quantitative question that is global, and I think it's just hard. So we've tried. So we have a proxy for what would be the magic angle for all of these materials here. And if the magic angle that you predict, so the angle at which the band becomes extremely flat, is above the relaxation angle, then you can trust it. It turns out that most of the time it's not in the good direction. So we don't have a good answer yet.
And just an unrelated question. I guess it's not circle theory, but it was the zirconium.
This is valence band. Yeah, the zirconium is conduction. Yeah,
For which you predicted threefold or fourfold increase.
Yeah.
Is that prediction verified yet, or someone?
Yeah, we're working on it because the superconductivity in the monolayer wasn't quite understood. So we need to go back to more ab initio. So what we have is something too phenomenological to. We look at density of state, we argue, but it's not good enough. Yeah.
That's it.
Yes.
I have some maybe conceptual question. So everywhere you had this quantum simulation, but how you're going to, I understand that you can control these states, but how you can do the operations?
The operation between
if you want to consider some of the states like qubits or whatever, then you need to do some operation on them.
Yes, so it's not a quantum computer yet, it's a quantum simulator. So it's an analog quantum simulator. So I would just want to simulate a phase that has quantized, okay, so this is a bit the condensed matter problem. We want to simulate things that we see. But yeah, so here it would be, can I simulate anionic phases? And that's a bit the outline. Then I think if you really want to go to the quantum computer side, there's, I think, one way to do it, which is you want to trap those anions and then do operation on them. Operation on anions is braiding them. So, right. So first you need to trap them, localize them, and then you need to move them around. I think you can localize them as follows. So create 2 copies of the state that we've just seen, ferromagnetic quantum Hall state, ferromagnetic quantum Hall state in the opposite direction. Approximatize it with a superconductor. Then at the boundary between the two, stem will be gapped and will host trapped anions on the corner of that boundary, of that line boundary. So that's the way you trap them. And then you need a way to move them around, which is even crazier experimentally. But you can think of you create the superconductor, the pair of fractional chain insulator, and then change, so you get copies here of Majorana, and by creating or destroying the superconductor, you can braid them around. So you can move this one here, do some operations there. So that was all the how Majorana were hoping to be braided with 1D wires. So it's the same, but with the generalization of Majorana, which are Z3 parafermions in that case. But this is too crazy. Yeah, no, this is crazy. No. this is crazy. No, that's why it's my backup slide. It's only if you don't want to believe me. I think you have good reason to be to not trust anything I say concerning designers. But there's also good reason to hope that there's something that will come up of those experiments, which is you want to proximatize a superconductor with a topological phase to create those anions. So that's the main theory way we know how to trap those things. And there's 2 experiments that have shown that you can do things like that. So with non-homogeneous gating, you can put 2 phases in close proximity. So, and those materials in their phase diagram sometimes have superconducting phase, sometimes have fractional topological phase. So here you could hope that inhomogeneous gating allow you to put a superconductor close to a fractional phase, which I think is much harder. So the second thing is by putting just a piece of palladium and letting it diffuse in your material, you form a pillar structure. And that pillar structure is actually superconducting. And that was shown in the book of Sanfeng Wu in Princeton. And the thing is here, they've already done that experiment on top of twisted MOTE2. So it's already what you need in practice. The superconductor is a good superconductor up to 1.7 Kelvin, something like that. And the only bad thing about the experiment is that you can't trap an anion with a superconductor and the 2/3 state. You need a slightly more, you need a different state to be able to trap this anion with a superconductor. And so you need a big architecture here to do it. But
You also,
yeah, I think that's hope. That's hope. Like this is crazy. Yeah, it's obviously hard. But it doesn't mean we don't have to think about this, right? It's
but in this case, you can't turn on or turn off the super.
yes, yeah. So that's the problem. So with the gate defined,